So, dear students, in today's lesson of MAT2611, we will discuss about the subspaces of a vector space. As in the last session, we saw about the vector spaces and its related things, but in the today session, we will see that what are the vectors, what are the subspaces, and which of the following sets are not subspaces. Actually, the vector space is a special class for which it's a vector space. And vector space are always deals with the two operators. One is the with the vector addition and with scalar multiplication. And now the question arises that if you have a vector space and if there is a subset of a vector space, then is it possible or under what condition if we check then its subset will becomes a again a vector space. So this is the definition of a subspace. Basically, subspace are also itself a vector space. But since if we know that the bigger set is a vector space, then its child set or its subset for its subset, we only need to check that to satisfy the condition under what condition the given set will be again a vector space. So for this, we consider this important definition like if W is a subset of a vector space V, like it is given that V is a vector space and W is its subset, then such a set W is called a subspace of V if W is itself a vector space under the addition and scalar multiplication defined on a vector space V. Like the same operations we need to use the plus and multiplication, but since we know that V is a vector space and we will satisfy all the axioms of a vector space, which are the around 10 conditions. But here we only need to check the two conditions. If it satisfies the only two condition and its parent space or its superset is a vector space, then it will become automatically a vector space or and also called a subspace of the bigger set V. Like V is a vector space, then W is also a subspace when W satisfies only the two axioms. Which are that important axioms? So look at this theorem, which state that if V is a set of one or more vectors in a vector space V, like V is a vector space and W is any non-empty subset, then W is a subspace of V if and only if it satisfies these two important conditions. The first condition is that if you take any two vectors U and V from the set W, then their sum is also in the set W. Like it is closed under vector addition. Like for any two elements of a W, the sum is also belongs to the W. And the second condition is that if K is any scalar and V is and U is any vector in W, then KU is also belongs to the W or KU is also in the set W. If set W satisfies only these two axioms, then automatically this W also becomes a vector space and we call it a subspace of the above its superset uh, V, which was given before as a vector space. Now there are the several examples and several things. So here I can tell you that if V is a vector space, then its subset if only satisfies these two conditions, then the rest of conditions will be automatically hold for a set V. So it means that we only need to test these two conditions and we get the conclusion that such a set is again a vector space and it's also called a subspace of a the given set whose for which this set is a subset of the the bigger set. Now let us see some examples that the zero subspace zero set is always a vector space and we call it a subspace. For example, in R set of all real numbers, we know that we have the origin 0 only. So this W is a set, it's contain only the one number 0. And this set is actually the subset of a R. if you take in R, and it's also in R square, the origin is a subset of a R square. Similarly, in R cube, the 0, 0, 0 point is a subset of a R cube. So these all kind of sets are a subspace of that particular sets, and this is very easy to check that since the 0 belongs to this set V, then if you take first element 0 and second element 0, then their sum is also 0, which belongs to again this set W. And if you multiply the any scalar k with the element 0 of that set, then 0 times k is equal to the 0, and that 0 belongs to this set W. It means this set W satisfies the both axiom, and hence this set will becomes a vector, a subspace of the given vector space V. Here, I also describe you such kind of things in the drill, like this set W is called a is a subspace of a vector space V if for all elements U and V belongs to the W, implies this the sum of its elements is also belongs to the set W. And if we take any vector U in the W, then k times U also belongs to the set W. And here, if we take the 0 set, which is a subspace of R, then 0 plus 0 is equal to the 0, which belongs to this 0. 0 bold mean a set having 0. And if we take any scalar k, so 0 times k is equal to the 0, and that 0 is also belong to this. Hence, we conclude that this set 0 is a subspace of R. In another example, we can see that suppose in R square we have a set W contains all those elements which are in the form of a pair x comma 0 belongs to the R square where x is any real number. This set is a subspace of R square. We can check the condition. For instance, if we take any two elements U and V belongs to the W, then U will be of the form U will be equal to x1 comma 0 and V is equal to x2 comma 0, where x1 and x2 are any real numbers. Now, if we add these two sets like U plus V, you know that U plus V, how to add? The U will be equal to x1 comma 0 and plus V will be the x2 comma 0. And we know that if we add the two vectors of two vector of same size, then first element will be added in the first and second will be added in the second. So it will become x1 plus x2 comma 0. X1 is a real number, x2 is a real number. So sum of two real number is again a real number. So it means this is again of the form of this kind. So it means that this is the element of again set W. So we conclude that whatever the vector U and whatever the vector V is that belongs to the W implies their sum is also belongs to the set W. Moreover, if we take any scalar k, then let's multiply k with u, then k times u will be equal to k can be 0 or positive or negative, whatever the value of k is. So k times the vector u is equal to k x1 comma k0. K0 is 0 because 0 multiplied with any vector is the same as k times 0 is 0. And again, we can see that this is again belongs to the W because the first element will be equal to the form of x k x1, and where x1 is a real number, and if you multiply k with again any real number, then it will be again a real number. And we have noticed that this again belongs to the W, means ku is also the element of W. So the both conditions are satisfied. Hence, we conclude that such a set W is a subspace of R square. Since R square is a vector space, we saw this thing before. Now the next thing is the next example. Let us consider that Z is a set having x, y belongs to the R square that satisfies the condition that 2x minus y is equal to the 0. Now, if we take let us check the first condition. Let us take z1 comma z2 belongs to the z, then z1 will be equal to the x1 comma x2 that satisfies this type of condition that 2 times x1 minus y1 is equal to the 0. And z2 will be of the form of x2 comma y2, where 2x2 minus y2 is equal to the 0, because z is the collection of all this form of elements. Now let's add these two elements, z1 plus z2. If we add these two elements, then it will becomes the x1 plus x2 comma y1 plus y2, where the sum of that element will be equal to of that form. So first, we if we add their components, then this right hand side will become 0, means 2 times x1 x2 minus y1 y2 is equal to the 0, because the first form it satisfies the above condition, and if we also add these two, then it will become 0 plus 0 is equal to the 0. It means this form of condition is satisfied, that this thing is equal to the 0, which means x z1 plus z2 belongs to the z. Now if we multiply any scalar k with z1, then k times z1 is equal to the kx1 comma ky1. Now if we multiply with the k on their the conditional parts of that one, so then k will be multiplied with each of its elements, and we know that 2x1 minus y1 is equal to the 0 as it's given in the condition or here. So it will become 0 times k times 0, which is equal to the 0. And it means that such x, such kz1 belongs to the z. Hence, z1 is the subspace of R square. So these are the examples for which if there is any condition available, we can check that still if we multiply with k with its element, then it will be part of the set or not. If it will be part of that set, whatever the k is, either positive, negative, or 0, then we conclude that this is closed under the scalar multiplication. And if the both conditions are satisfied, then we conclude that such a set Z is a subspace of a given vector space. Like this is the subset of R square, so it means that this Z is a subspace of R square. So remember that since every set have a subset, similarly every vector space have a subspace, and subspace are itself a vector space. So since vector space satisfies the 10 axioms, here we don't need to check the 10 axioms. Only we need to check the two axioms of that one. Then it still becomes a vector space. So it means that when we know the parent space or it's a superset is a vector space, then in the child set or in it's a subset, we only need to check the only two properties. If these two properties are satisfied, then it means given set will becomes again a vector space, and by default it will satisfies the all other 8 properties of a vector space. Now let's see another example, which will determine whether this set Y is a vector space or not. So here, if we take any two elements, Z1, Z2 belongs to the Y, then Z1 will be of the form that X1, comma Y1, where 2 times x1 minus y1 is equal to the 0. Look, we are taking this condition that whenever the elements are of that form, so it must will be satisfy its condition. And z2 will be of the form of that 2x2 minus y2 is equal to the 0. Now let's add its components like z1 plus z2. If we add that one, then it will becomes what? 2 times the sum of its first entry minus y1. Y1 will becomes y1 plus y2. Y will becomes y1 plus y2. And note that if we make it separable that one, so 2 times x1 minus y1 is equal to the 1, and 2 time x2 minus y2 is also equal to the 1, and 1 plus 1 is equal to the 2. But remember that it contains only those elements for which 2x minus y is equal to the 1, not equal to the 2. So it means such a z1 plus z2 does not belongs to the set y. So it means first condition does not hold. If we need to show that if it's not a subspace, so only the one condition will be sufficient. If you can also check that maybe second conditions hold or not. but it is sufficient to show any one of that. If any one of the condition is not satisfied, then it is sufficient to conclude that such a set Y is not a subspace of R square. And here you can see that second condition is also not satisfying. For instance, if we take any scalar k is can be zero, positive or negative. Then and z1 belongs to the Y. Then if we multiply k with z1, then it will becomes equal to the kx1 comma ky1. Now let's check that kx1 comma ky1 will be satisfied this kind of condition or not. So if we multiply the 2 times kx1 minus ky1 is equal to, the k will be equal to common, then if you take the k common, then here it will becomes 1. And 1 times k is equal to the k, and that is not equal to again the 1, because you know that the k is not equal to the 1 always, because 2 times x1 minus y1 must be equal to the 1, then it will satisfy this condition. But here the k is arbitrary and it is satisfies this condition for all values of k. For example, if we take the k equal to 0 or k equal to 1 or k equal to 2, then this is not satisfying. This is satisfying only when the value of k is equal to, you can just fix the k equal to 1 only then. So it means k times z1 is not belongs to the Y, and hence Y is not a subspace of R square. This is also the nice example, like if we take another set M equal to x comma y, it belongs to the R square where x is greater than 0, y is also greater than 0. And let us take the two of its element. M1 is x1 comma y1, where x1 is greater than 0 and y1 is also greater than 0, and m2 is equal to the x2 comma y2, where x2 is greater than 0 and y2 is also greater than 0. Now if we add m1 plus m2, then it will becomes x1 x2 plus y1 y2. And remember that x1 is non-negative, x2 is also non-negative. The sum of two non-negative is also non-negative. The y1 is non-negative, y2 is non-negative. The sum of y1 and y2 is also non-negative. So hence m1 plus m2 satisfies this condition that both of its elements are greater than or equal to 0, or both are non-negative. So m1 plus m2 belongs to the M. But what about the second condition, that when we multiply with any k with the element of any element of the set M, then will it satisfies that k times M belongs to the capital M or not? If we multiply the minus 1 with m1, then it will becomes minus x1 minus x2. And remember that if x1 is greater than 0, x2 is greater than 0, then minus x1 and minus y1 are not greater than equal to 0. They if like if we take 1 from that, so minus 1 does not belongs to the M if you multiply with minus 1. Similarly, if you multiply with minus 2 with some element like 1, then it will becomes minus 2 comma minus 2, and minus 2 cannot belongs to that set M, because it contains only those elements where x is greater than 0, greater than or equal to 0, and y is greater than or equal to 0. So hence it means the first condition is satisfied, but second condition does not satisfy. So we conclude that M is not a subspace of R square. Okay, now let's come to see another example, that what happened in R square if we take this example, that U is a subset of R square where 0 does not belongs to the this set. Like it's contain all the element x, y belongs to the R square where x is not equal to 0 and y is not equal to the 0. Now we can check that, like if we take k equal to the 0, then k times u is equal to 0 times x1 y1, and 0 times x1 y1 means 0 multiply with x1 and 0 multiply with y1, that is equal to the 0. And note that this 0 0 does not belongs to the set U, and hence we conclude that this set U is not a vector space. Here one can note that this satisfies the first condition but not the second condition. Similarly, for some vector space it satisfies any one of the condition but not the other condition. Here we can see that if U1 and U2s are if we have a set like U1 plus U2 where U1 and U2s are the collections of any two subsets, then we can prove that the sum of two vector spaces is a vector space. For instance, if R1 and R2s are belongs to the U1 plus U2, then R1 will be equal to of that form, and R2 will be also satisfies this condition. Then if you add both, then the sum will be equal to of this form, where the first element belongs to the U1 and second element belongs to the U2. So R1 plus R2 belongs to the U1 plus U2. Similarly, one can show that K times R1 is also belongs to the U1 plus U2. And moreover, the intersection of two subspaces is a subspace. So this kind of a subspace, the results are useful. Moreover, if V is a vector space or V is a subspace, here we can see that if V is a vector subspace, then one can show that V plus V is equal to the V. Like here the proof is available. For instance, if we take V belongs to the capital set V, then we can write V as a V is equal to V plus 0. And the first V belongs to the capital V and plus 0 belongs to the second V. Since V is a vector space, so 0 always belongs to that. So it means initially V belongs to the capital V. Now this set V belongs to the capital V plus V. Hence it means such a V is a subset of V plus V. Now, secondly, again, let us take such an element U belongs to the V plus V. Then it means U will be equal to the form of U1 plus U2, where U1 and U2s are coming from the set V. Now we can write as a U is equal to U1 plus U2. Remember that the sum of two elements of a vector space is also belongs to the vector space. So it means such a element U belongs to the V. Now initially U belongs to the V plus V. Now U is belong to the set V. It means this set V plus V is a subset of V. Now from 1 and 2 we conclude that V plus V is a V. So this is a small proof and interesting proof you can see about that one. And there is another example regarding the subspace that the P2, the collection of all polynomials of degree 2 is a subspace. For example, if we take the P1 and P2s are the two polynomial of degree 2. Degree 2 means it satisfies the quadratic equation for all x. Px is like a function where x is coming from the R. And A1, A2, A3s are the real number. Now, if we take P1 and P2 belongs to the this set P2, then if you add its elements, then its element will becomes in that form where these are the constants like A1, A2, A3s are constant, A1 tilde, A2 tilde, A3 tildes are constant. So if you add them, then one can express this into that form. So it will again becomes a polynomial, like because we know that sum of two polynomials is a polynomial, and hence it belongs to the P2. The sum of two polynomial is a polynomial, and hence this is also the second degree polynomial, where these are the again becomes the coefficients of a that polynomial. Now, similarly, we can see that if we multiply k with px1, where p1x is a polynomial of degree 2, then if you multiply k with that, then it again becomes a polynomial of degree 2. Hence, it means it satisfies the both conditions of a subspace. So we conclude that P2 is a subspace of P3, P4 up to so on. And here, we can see that this can be extended as a general. P1 is a polynomial of degree 1. So it means any A1, A2, if we take a polynomial like A1 plus A2x, it belongs to the P1. And A1 plus A2x is equal to, we can write as A1 plus A2x plus 0x square, that belongs to the P2. And similarly, A1 plus A2x is, one can write as A1 plus A2x plus 0x square plus 0x cube, that belongs to the P3. So it means P1 is a subset of P2, P2 is a subset of P3 up to the Pn, polynomial of degree n. So this is the relation, and it means that P1 is a subspace of P2, P2 is a subspace of P3, and up to so on. So this is the relation which always satisfies between these polynomials. Okay, then let us see also some other examples regarding that. So, for instance, these are the also examples of a polynomials. For instance, if we take z as a set x, y, z equal to 2x equal to yz, is a subspace of R cube or not, because this it contains the triplet element. So here remember that one can check as a, if you take any two elements of Z which satisfies this relation, like 1 to 1 belong to the Z, because it satisfies this condition that 2x equal to yz, mean first element multiply with the 2, then it is equal to the multiplication of second and third element. So it satisfies this condition. Also, if you take another element x2, y2, z2 belongs to the z, then it's also, this element is also belong to z, because it also satisfies this condition. Now, if we add these twos, then it will becomes uh, if we add these two vectors, then it will becomes 2, 3, 3. Now note that it satisfies this condition or not, like 2 times x equal to yz. So here we have 2, 2, 3. So 2 multiplied by 2 is equal to the 4, but 3 multiplied by 3 is 9. So 4 is not equal to 9. It means the sum of two vector is not giving us this condition that 2x equal to yz. And hence we conclude that the sum of two vectors, the sum of two vector does not belongs to the z. Hence, this z is not a subspace of R cube. Similarly, one can check on the other one, like one can see the counter examples of that. If we take the element z belongs to 1 to 1 belongs to the z, then if we multiply k for k equal to 2 or any specific value, then one can check that this does not satisfies this condition that 2 times k x belongs to the Z, like it doesn't fulfill the condition of this. So it means Z is not a subspace. So again, I am telling you that for making the counter example or for showing that any one of condition is not satisfied, it will be sufficient to show that such a set is not a vector space. So if any one of the above condition is not hold, then we conclude that this set is not a subspace. Again, this is another form of a set, like x equal to 2y and y plus z is equal to the 2. The example is available over here, and one can easily check that this set is a subspace, because sum of two vectors, the sum of two vectors belongs to the set Z. And if you take any z1 belongs to the Z, then k times z is also belong to the Z. Hence, such a set such a set Z is a subspace of R4, because it contains the elements of a R4. Now, another example, so I will upload this one into the portal of a MAT2611 in 2024. So you can see these notes and the details. This example is also the example for which you can determine that is this set is a vector space, is a subspace of R4 or not. Here the proof is available. And remember that there are some examples for which these are not a subspace. Like in R4, if we take this set, Remember, if there is some square or under root or something will happen or product of the entries, then they will never be a subspace. It cannot fulfill the condition. When you will make a checking of that, you can see that it will not closed under the vector addition as well as not this. If you multiply k with z, then such a k z does not belongs to the z. So both condition will not be satisfied. Similarly, the product is not allowed, like x, y, if you take x, z or whatever the multiplication, then this will never become the subspace. Moreover, the constant is 1 is not allowed. Then like if there will be any number other than 0, then it will never becomes a subspace. So here must be the element, this element must be 0 or should be removed from that. Otherwise, you know, x plus y, if you take plus 1 and again uh, u plus v equal to 1. So x plus u plus y plus z is equal to becomes 2. So here instead of 1 it will becomes 2. Then it will never becomes a subspace of R3. Similarly, if you take square root of that, then it will never becomes a subspace. X plus y equal to z. If this condition is happening, then such a set will becomes a subspace of R cube. And similarly, if you have a set Z for which x, y, z, it's a collection of all x, y, z where x equal to 2y and y equal to the 4z. Then this set will becomes a subspace of that. Again, I'm telling you that whenever we want to show that or we got that such a set is not a subspace, so we need to only show the counterexample or need to show that any one of the given condition is not satisfying. Then that will be sufficient to show that such a set is not a subspace. But in case if a set is a subspace, for that case you need to show the complete proof, like it is the sum of two vectors are also belongs to that one, and also if you multiply k with any vector of that one, so k times that vector is also belongs to the that set. So it means such a set is a subspace of a the its super set, which is a vector space. So this is the topic of vector space. Here, if we comes towards the assignment problem, so here the question number 9 is only related to that one. Determine whether the set U and V are subspaces of R4. So U is a set X, Y, Z, comma 0 belongs to the R4, where X plus Y equal to the Z. And V is a set X, Y, Z, U belongs to the R4, where X equal to 2Z and Y is equal to V plus 1. So need to determine that which of the following is subspace of R4 and which of the following is not a subspace of R4. And the linear combination, linearly dependence and independence, we will see this on Monday class. Okay, on the Monday, we have a one class from 4 to 5, and in that class, we will study about the linear combination, linearly dependence and independence, and these the problems related to that topic. So today in this session we covered this topic. Similarly, the class of all continuous functions and space of all continuous functions are subspaces. So these are some examples of that one. So I will upload these notes for you in the Moodle My Module website, and you can easily go through from that. If you have any question regarding the topic, you can ask your question, please. Dear student, do you have any question regarding this topic? Regarding the linear combination, linearly dependence, independence, spanning, we will discuss this on the Monday class. Okay, I will send you the link and also upload the link on the My Module website. So this topic we will study from 4 to 5 on Monday. Yes, please.
So can you hear me?
Yes, I can hear you. Yes, go ahead, please.
All right. So can you please repeat example? I believe it was example 6, 7, or 8. The last example before
Which one?
the one that has functions.
In this book, like this one?
Yes, sir. No, no, no. In your notes,
Okay.
the one before that, sir. Okay, please go down.
Here you mean the on the polynomial you mean, or which one?
The example where that one said the one with four dimensions or four coordinates.
This one?
That one, sir.
Okay. So here you know that Z is a subset of R square because you know the R4, because in R4 we have the elements of a four tuples. But Z contains only those elements where the first element is equal to the 2 times of y. Like if this is 2, then y must be 1. You know, it satisfies this relation. And moreover, the y minus 4z is equal to 3u. Now, need to show that is the sum of two elements of z is also belongs to z or not. Now, if we take z1, comma z2 belongs to this capital Z, then z1 must be of the form of a some x1 y1 z1 comma u, where x1 equal to 2y, because you know 2y1, because x is always equal to the 2y, because this z1 belongs to the capital Z, so it must satisfy these relations. And y1 minus 4z1 is equal to 3 u1, so it satisfies this relation. Moreover, similarly, z2 is also belongs to the is of the form of a z2 will be equal to the x2 y2 z2 and u2, and having satisfies this relation. Now let us check that what happened if we add z1 with z2. Now z1 plus z2 is the value vector of z1 plus vector of z2, and we know that it will be equal to the first element is always add with the first one, second element will add in the second, and third is will be add in the third, and element will be add in the fourth, because it's a vector addition, the simple method of a vector addition. Now let us say that x1 plus x2 we call it say x3, y1 plus y2 we say its name as a y3, because we know these are real numbers and sum of two real number is a real number. Similarly, z1 plus z2 or z1 is a real number, z2 is a real number, and sum of two real numbers is a real number, so we say its name as a z3. u1 plus u2 we call it u3. Now let us check that is these elements also satisfy this relation or not, because if these elements satisfy this relation, then it means z1 plus z2 belongs to the z, because these are elements coming when we add z1 plus z2. Now now let us see that what happened when we add x, is it satisfy x equal to 2y or not. So remember that x3 is equal to what, x1 plus x2. Now x1 plus x2, if we check its value, x1 is the 2y, x2 is the x1 equal to the 2y1, x2 is the 2y2. So it will becomes 2y1 plus 2y2, because the put the value of x1 as a 2y1 plus y2 is equal to x2 is equal to 2y2. Now if we take 2 as a common, then it will becomes y1 plus y2. And remember that what is the y1 plus y2? y1 plus y2 we
Y3.
call at a y3. Remember that y1 plus y2 is a y3 over here. So similarly, so it means that we saw here that x3 is equal to 2 times y3. So it means this relation is satisfied, like first element is equal to the 2 times of second element, second component. So it means x3 is equal to 2y3. Now let us check that is the sum of elements also satisfies this condition or not. So for this, let us take 3y3 minus 4z3. So y3 is what? Y1 plus y2 minus 4 is the same, and but z3 is z1 plus z2. Here these are defined that z3 is the z1 plus z2. Now if we add this, we can make it separate, that we can write as a y1 minus 4z1 plus y2 minus 4z2 in this way. Then remember, as a we these elements satisfies this relation that y1 minus 4z1 is what? Is 3u1. So we just put the first as a 3u1, and the second y2 minus 4z2 is equal to 3u2. So we just take 3 here, just write 3u2 over here. So if we take 3 common, then it will becomes u1 plus u2. And remember that over here, what is u1 plus u2? u1 plus u2 is u3. Now it means that the 3y1 minus 4z3 is 3u3. Like second element minus 4 times third element is equal to the 3 times fourth element, because this is the relation which holds that the second element. So our objective is to satisfy these relations for the values of that. It means z1 plus z2 satisfies these relations. So z1 plus z2 belongs to the set z. Hence, we conclude that the sum of two vectors of a z is also belongs to the z. So it means z is closed under the vector addition. Similarly, if we multiply k with the element of z, so like z, if as z belongs to the capital Z, so z1 k multiplied with z1 will becomes that, and if we multiply k1 with x1, then it will becomes 2 times ky1. So it means the first relation is hold. First of this relation is hold that k times x1 equal to 2 times ky1. And moreover, if you multiply k with the second element, like the ky1 minus 4kz2 is equal to 3k u1. So the second relation is also hold. So it means k times u is also belongs to the u. Now if the as we notice that the sum of two vectors of z belongs to the z, and if we take any scalar k and multiply it with any vector z1 belongs to the z, then kz1 also belongs to the z. So both conditions are satisfied. Hence, we conclude that z is a subspace of R4. So basically, this is the technique, and when you make a practice, then you will really see that what happening that the collection will satisfies these two relations, and this is very important. Again, I am telling you that we know that R4 is a vector space, and if its subset satisfies only two conditions, then automatically this set is also becomes a vector space. So we not need to check all the 10 conditions, only that these two conditions are sufficient to show that this set Z is a vector space or not, itself a vector space or not. But again, I'm telling you, just we need to, it's important to check that first we make sure that is it's a subset of some set which is a vector space or not. If we know that its superset is a vector space, then for this set only need to check these two conditions, and if these two conditions are satisfied, then by default this set will becomes a vector space, and we call this set as a subspace of a the its superset. Okay, is there any other question? Yes, please. Okay, this is the interesting topic. I hope when you make its practice, then your concept will be clear. Otherwise, you can ask your question by email or also in the Telegram. So on Monday's session, we will see about the linear combination, linearly dependence and independence, and also the spanning. Then it will comes towards the basis. Basically, that will describe the inside structure of a elements of a vector space and subspaces. Okay, I hope if there is no question, then we can stop the session of this one. And okay, goodbye and many best wishes.
Thank you, sir. Bye bye.
Okay, goodbye.
Thank you, Professor.
Thank you,
Thank you,
Prof.
Professor.